All right, we are going to move on to our next lecture here. This is Chapter 3, Lecture number 2 for Ralston Valley High School's AP Chemistry class. In this lecture, we're going to be discussing the mole map, the idea of percent composition by mass, and empirical and molecular formulas. All of these concepts have been introduced to you last year during your first year chemistry class. We will make them obviously a little bit more complex, especially the idea around empirical and molecular formulas as we get towards the end of this lecture. But let's go ahead and get started. So here we are back at your familiar and beloved mole map. Recall this mole map is a tool that allows us to quickly and rapidly convert between different common laboratory measurements we might want to make, including mass, volume, and number of particles of a substance. And the key central idea linking all of those ideas is that concept of a mole. Recall from last year that we defined a mole as being the number of particles in exactly 12 grams of carbon-12. That is Avogadro's number of 6.022 times 10 to the 23rd particles. An enormous number of particles. And recall again, the reason why we chose that number in particular is because with that value, the mass of either 1 mole of protons or 1 mole of neutrons essentially comes out to be about 1 gram or so, which means it's a very useful link between that idea of the average atomic mass of an atom and the molar mass, that is the mass of 1 mole of those atoms. By setting Avogadro's number equal to that value of 6.022 times 10 to the 23rd particles, that means that when we measure out 1 mole of particles, we end up with a mass in grams, which is the mass reported on the periodic table. And that's the same thing we get if we find the average atomic mass of an atom in units of AMU. So it's just a very useful counting number for us to use. And it also happens to be the tool that allows us to convert between macroscopic scale laboratory measurements we can make easily with our equipment in the lab, things like masses or volumes, and atomic scale measurements that are much more complicated and difficult to make about numbers of atoms or particles or molecules. So looking at this mole map, recall from last year, we had different conversion factors we used to go between those different little boxes on our mole map. The first conversion factor, and probably the most commonly used one, is to convert between units of grams, that is a mass, and units of moles. In order to make this conversion, we would need to know how many grams per mole there were of a particular substance. And obviously, that grams per mole is a familiar concept. That's the molar mass of the substance. So our conversion tool between those two boxes is the molar mass. We could memorize when you multiply and when you divide, but rather than doing that, I would like you to just be in the mindset of setting up your dimensional analysis monorails in order to make those calculations so you're not making mistakes about multiplication and division. If you just pay attention to your unit analysis, a monorail will help you get to the correct answer for making those conversions quickly and easily. That's our first conversion there. The second conversion we use often in class is between moles and a number of particles. On the right-hand side of our mole map over here, if we wanted to convert between a certain number of particles and a number of moles, we would need to know how many particles per mole there are. And obviously this is a straightforward idea because by definition, the number of particles in 1 mole is Avogadro's number of 6.022 times 10 to the 23rd particles per mole. So Avogadro's number serves as our conversion factor between particles and moles on that section of the mole map. Remaining on our mole map now, we have 2 volume measurements. The first of those is the volume of a gas under standard temperature and pressure conditions. And as you all remember, both from our discussion of moles last year, as well as from our discussion of gas laws, the molar volume of a gas is equivalent to 22.4 liters per mole as long as we are under standard temperature and pressure conditions. That is standard temperature of 0 degrees Celsius and standard pressure of 1 atmosphere of pressure. And again, this is independent of the identity of the gas. All gases occupy the same volume under a given set of temperature and pressure conditions. So we've got our molar volume of the gas of 22.4 liters per mole as a conversion tool between volumes of gases and moles. And last but not least, down at the bottom right here, if we want to convert between a volume of a solution and a number of moles of solute particles, we would need to know how many moles of solute per liter of solution were present. And that idea of moles per liter is a very familiar one from last year. That is a measurement of concentration that you all know and love, which we refer to as molarity. So our molarity is a conversion tool that allows us to convert between moles of solute particles and volumes of solution. By definition, again, molarity is moles per liter. And again, rather than thinking about when you multiply and when you divide in all of these different scenarios, I'd just like you to come at these from the perspective of setting up your monorails to make sure your units cancel out properly, because that's a way that you'll always make sure your unit conversions work properly for these mole map problems. So with that set of conversions now set for our mole map, let's do a real quick just example for argument's sake here. Let's say I wanted to determine the number of molecules present in 100 grams of water. Thinking about my mole map as a kind of tool that guides me from where I start to where I want to end up, I'm going to want to start here in units of grams, which is what I've given you of 100 grams of water. And I want to end up over here at the number of molecules of water. And you'll note here that the pathway I need to take goes right through the center there. I need to get moles first. So the sequence of conversions I'm going to make is I'm going to convert from grams of water into moles of water. And to do that, I would need to know the molar mass of water, which, as it turns out, I do know from multiple times I've calculated it before. It's 18.01528 grams of water per mole. Once I then had number of moles of water, I can convert from moles into molecules by using Avogadro's number in my pathway there. So let's go ahead and set up together here our monorail. And as we do that, I'm going to start off with the given value of 100 grams of water. Down in the bottom here, to cancel things out properly, I need units of grams. So I'm going to use my molar mass of 18.01528 grams of water per, and again, remember grams per mole is a ratio, so I'm going to use my central line of the monorail there as a dividing line. 1 mole up top there. And then down at the bottom, to cancel out units again, per 1 mole of water molecules, up top there are 6.022 times 10 to the 23rd water molecules. And when I go ahead and cancel out units, multiply out everything across the top and divide by everything along the bottom there, I end up with a final answer, which comes out to be, it looks like about 3.34 times 10 to the 24th water molecules, which is a tremendous number of water molecules indeed. So that's how mole map calculation goes. You should remember those from last year. Another idea you should be familiar with from last year is the idea of a percent composition by mass. You might remember last year we did the bubblegum lab in which we determined the percentage of sugar in those samples of double bubble bubblegum. And we're going to have a quick look at this idea again here just to refresh your memory about how we make this calculation. The percent composition by mass can actually be determined via a number of different actual laboratory methods in terms of how we would actually calculate that data. One thing we might think about doing would be to undergo a sequence of chemical reactions, massing both the reactants and the products. And in particular, if I started off with a compound, which I would mass as an initial reactant, and then I decomposed that compound into its constituent elements, which then would be collected separately and massed separately. Because of conservation of matter, I would expect to see that the sum of the masses of all of the products that we had decomposed into must have been equal to the mass of the compound we started with. And I could simply divide the mass of each element that we obtained this way by the total mass of the compound we started with and multiply by 100% to find the percentage mass of that particular compound. Alternatively, we could use mass spectrometry. We introduced you to that idea of a gas chromatography mass spectrometer last lecture in the start of this chapter here. and recognize that by looking at those different atomic masses on the mass spectrometer readout, we can really figure out what elements something is actually made up of, and kind of work our way backwards from there. So there are ways in the laboratory where we can determine the percent composition in a slightly more accurate sense than we did by simply chewing gum like we did last year and subtracting out all the sugar mass. When we're calculating a percent composition by mass, there's two different ways we can go about making this calculation. The first thing we could do is to simply, as we mentioned, use the definition of percent composition, that is, to divide the mass of each element present in the sample by the total mass of the sample itself, and then multiply it by 100% to express that as a percentage. This way works really, really well when dealing with those decomposition reactions we just discussed moments ago. So that's essentially using the definition to make a calculation. Alternatively, we can also calculate a percentage mass from the formula. That is, I could simply calculate the overall molecular mass of the compound, and then out of that, I could kind of pull out the masses of each of the individual elements that contributed to that overall mass of the compound and divide the masses of each element by the overall mass of the compound to figure out the percent mass in that fashion. And we'll have a couple of examples of each of these methods on the next slide, so keep watching. So let's go ahead now and work a couple of real quick percent composition example problems. The first of which is a type of problem that we would expect to see if we were dealing with, let's say, data from decomposition reactions for this particular compound of iron and oxygen. So example 1 is asking us to determine the percent composition by mass of a compound that yields 35.5 grams of iron and 15.0 grams of oxygen upon decomposition. Super easy problem right here. All I have to do is to take the mass of each individual element, starting with iron, of 35.5 grams of iron, and divide it by the total mass of the substance that we must have started with. And to find that, using simply conservation of matter, I could add together the 35.5 grams of iron and 15 grams of oxygen to tell me that the initial compound must have had a mass of 50.5 grams. So 35.5 grams divided by 50 grams total, multiplying that by 100% gives me my percentage of iron in this compound that turns out to be 70.3% iron. And by process of simple subtraction then, I could take the 100% that I know the total compound's mass is and subtract from that the 70.3%, which was iron, to find my percentage of oxygen. Or alternatively, I could simply divide 15 grams of oxygen present by the 50.5 grams total for the compound, multiply by 100. Either of those two methods gets me to my final answer for the percentage of oxygen of 29.7%. So real quick and easy way to calculate percent composition. For example number 2, let's go ahead and find the percent composition by mass of the compound hydrogen sulfide. Now note here that I don't tell you how much hydrogen sulfide we're dealing with because it doesn't matter. That is, percent composition by mass is an intensive property of a compound. It doesn't matter how much of the substance there is because of essentially Dalton's law of definite proportions, which we discussed last year. So let's go ahead next and make a calculation of the molecular mass of hydrogen sulfide, H2S. The molecular mass of hydrogen sulfide we can find by multiplying 2 times the mass of hydrogen of 1.00794 grams per mole. And when I multiply that out, that gives me 2.01588 grams of hydrogen in 1 mole of our hydrogen sulfide. And next, let's have a look at sulfur. Sulfur, there's 1 mole of sulfur atoms in 1 mole of hydrogen sulfide, and that would give me a mass of 32.065 grams of sulfur in that compound. Adding those together would give me a mass per mole of 34.08088 grams per mole. So I know the overall molar mass of my hydrogen sulfide. Now I simply have to pull out each of those different components I used to calculate the molar mass to find the percent composition. So of that 34 or so grams of hydrogen sulfide that was comprising 1 mole, only 2.01588 grams of that were made up of hydrogen. So I can simply divide that value by the overall total mass of the compound of 34.08088, multiply by 100%, and that gives me a percentage of hydrogen in hydrogen sulfide of, by my calculation, 5150% hydrogen. And again, I could simply subtract 100 minus that value to get my percentage of sulfur. Or alternatively, I could take the 32.065 grams of sulfur in the mole of that hydrogen sulfide compound, divide it by our overall molar mass of the 34.08088, and multiply by 100 to express that as a percentage again. And in doing so, I end up with a percentage of sulfur of, by my calculations, 94.085% sulfur. So either way we go about calculating percent composition by mass, it's a fairly straightforward process. But the real power of percent composition by mass isn't just to know it in and of itself. It's that we can use percent composition by mass measurements in the laboratory to help us determine the actual formula and therefore identity of a compound we're dealing with. And we'll do that on our next slides. In order to determine the identity of a compound in a laboratory, it can be very, very useful to start with percent composition data and use that percent composition data to determine what we refer to as the empirical formula of a compound. That empirical formula of a compound, as we discussed last year, is the smallest whole number ratio of the elements to one another within the compound formula. We can determine an empirical formula using the steps outlined on this slide here. And again, this is a process we went through last year, so this should be familiar. The first step in our process is, if we're starting with percent composition data, we're going to begin by assuming a useful amount of the substance for our calculations. Because percent composition is a intensive property, that is, it doesn't matter how much of the substance we have, we're free to make use of any amount of it if it will help our calculations be easier. And I would suggest that because we're dealing with percentages, a really easy amount to deal with would be to assume that we're dealing with a 100-gram sample. So if I then know the percentage of each element in that sample, I then also would know the masses of each of the different elements present. So for example, that we did a couple of problems ago, we found that our percentage of iron was right around 70%, which means out of a 100-gram sample, we would have 70 grams of iron. So first step, we convert percentages into masses by assuming a 100-gram sample. The next step is we're going to convert from the masses of each of the different elements in our sample to moles. We'll use a monorail here and our mole map in order to convert from mass to moles. And remember, the conversion factor we need here is going to be the mass per mole, or the molar mass of each of those different elements, easily found on your periodic tables. Once we have found the different numbers of moles of each of the different elements in our compound, we then will know a ratio of the different moles to one another. But because we're expressing this as a whole number ratio, we are going to need to make a division next in order to set all of the proportional ratios of the elements to one another to some sort of whole number ratio we can compare them to. And the easiest way of doing that would be to just look at the number of moles of all the different elements present and simply divide all of those number of moles by the same smallest number of moles present in our compound. So you remember that step we called that last year the divide by small step. And again, and the net effect of this is to simplify our molar ratios within the compound relative to a whole number value. So once we have done that step, the next step is, if we still have some of those ratios that are not whole number ratios to one another, like let's say, for example, if we have a 1.5 to 1 ratio, at that point we're then going to multiply all of the different numbers of moles present in the compound by some common multiple until we end up with a whole number for each of the different elements present in our sample. So again, like if we had a 1.5 to 1 ratio of oxygens to iron, I could multiply all of those by 2, which would give me a 3 to 2 ratio, which we would then be able to express within a formula of a compound. So that's our steps. We easily remember the steps for empirical formula because it rhymes nicely. We do percent to mass, mass to moles, divide by small, and times till whole. And by following those steps, please again note that what we are finding here is the empirical formula of the compound. That is the smallest whole number ratio of the elements to one another within the formula unit of the compound. That being said, that might be different from the actual molecular formula of the compound. So to make a distinction between those two, we need one additional piece of information that we'll see on our next slide. So whereas the empirical formula is the smallest whole number ratio of the elements to one another within the compound, the molecular formula is the more familiar thing we see, which is the actual formula of a unit molecule of a particular species, not necessarily expressed as the smallest whole number ratio of the different elements to one another. For example, a familiar molecule which is present in photochemical smog is the species NO2, which is nitrogen dioxide. Nitrogen dioxide also can react to itself in a dimerization reaction to produce another compound, which is dinitrogen tetroxide, N2O4. Both nitrogen dioxide and dinitrogen tetroxide have the exact same empirical formula. That is, the smallest whole number ratio we can express those elements to one another in is a ratio of 1 nitrogen to 2 oxygens. But dinitrogen tetroxide molecules actually are composed of 2 nitrogens bonded to 4 oxygens within the unit molecule. So that's what we mean by a molecular formula, the actual formula of the molecule unit itself, not the whole number ratio expressed as the smallest whole number ratio. So in order to determine the actual molecular formula, we need one additional piece of information. After we've gone through and found the empirical formula, the next step is to go through and calculate what's referred to as the empirical formula mass. That is the mass of 1 mole of that empirical formula unit. And we're then going to compare that empirical formula mass to the molecular mass. And when we do that, we're simply going to divide the molecular mass by the empirical formula mass. And if we do that, we should end up with some sort of small whole number ratio, which essentially comes up as a multiplication factor. And all that remains then is to take that multiplication factor and multiply each of the numbers of each element in the empirical formula unit by that same factor, and we'll end up with the molecular formula for our substance. Let's go ahead and do an example of that process using those exact nitrogen compounds I was just referring to on our next slide. So for this example problem, we're going to go ahead and determine both the empirical and the molecular formulas of a substance that is comprised of 30.4% by mass nitrogen and 69.6% by mass oxygen. And we've also been given here that the molecular mass of this particular substance is 92 grams per mole. So let's go ahead and do our steps for the empirical formula process first. Our step number 1 was to convert those percentages into masses. And again, the easiest amount to deal with in this, because we've been given percent composition data, is a mass of 100 grams, of which 30.4 grams would therefore be nitrogen due to the percentages we've been given. So if I have 30.4 grams of nitrogen, and I want to next convert that number of grams into moles, I'm going to set up a real quick monorail here. Monorail. And we're going to go ahead and convert from grams of nitrogen into moles by dividing by our molar mass so that units cancel out, dividing by 14.0067 grams of nitrogen per 1 mole of nitrogen gives me, in this particular sample of our compound, 2.17 moles of nitrogen present. I can then follow the exact same process for our oxygen. Out of the 100 gram sample, 69.6 grams of that would have been oxygen due to the percentage present. So we went percent to mass and then mass to moles. We'll divide that 69.6 grams of oxygen by 15.9994 grams of oxygen per mole. And that will yield here 4.35 moles of oxygen present in our sample. So we now have a molar ratio that is 2.17 moles of nitrogen to 4.35 moles of oxygen. But this is not a whole number ratio. So in our steps, we went percent to mass to moles. The next step is simply to divide by the smallest number of moles present, which in this case is that 2.17 moles of nitrogen. So if I divide all of those number of moles by the common value of 2.17, I see I end up now with a ratio of 1 mole of nitrogen to every 2 moles of oxygen. So therefore, I know my empirical formula of this particular species must be NO2. Now, that's the empirical formula. It could very well be a different molecular formula, though. And so to get to the final answer here for our molecular formula, I now need to deal with that molecular mass. Using my empirical formula of NO2, let's go ahead and calculate the empirical formula mass of this substance. So I'm going to calculate an empirical formula mass by multiplying the 1 mole of nitrogen by 14.0067 grams per mole, which obviously gives me 14.0067 grams of nitrogen. And then we had 2 oxygens present there, times 15.9994 grams per mole of oxygen. We can add those values together, and we end up with an empirical formula mass of 46.0055 grams of this substance per mole of that empirical formula. Now, that again is the empirical formula mass. I now need to find my multiplication factor. And I find that factor by simply dividing my molecular mass by the empirical formula mass. So we'll divide our 92 grams per mole by our 46.0055 grams per mole. And we see here that that really tells me then that my molecular formula has a mass which is 2 times larger than the empirical formula mass, which means my common multiplication factor is a factor of 2. So I'll then simply take my empirical formula of NO2, multiply all the number of species present by the multiplication factor of 2, which gives me a molecular formula of N2O4. That is dinitrogen tetroxide. So we can now find an empirical and a molecular formula. So to end up this lecture, a number of occasions you've heard me say that we've already introduced this idea to you last year. Well, here's where we're going to step it up a notch here. This is kind of an AP level problem relating to empirical and molecular formulas. In this particular example, we're not simply going to ask you to go through and follow the procedural steps we've shown you to find the empirical and molecular formulas. We're going to give you a scenario which is going to require you to do some logical thinking and apply that idea to the concepts of empirical molecular formulas in a more nuanced way. So what we're going to ask you to do here is to determine the molecular formula of an unknown carbohydrate. Carbohydrates are compounds which contain the elements carbon, hydrogen, and oxygen. And what we're going to give you as given information is that we're taking a 0.360 gram sample of this carbohydrate and burning it in atmospheric air, producing 0.520 grams of carbon dioxide and 0.216 grams of water vapor as a result. And we'll give you the molecular mass of this carbohydrate is 180 grams per mole. Now, the first place to start here is to have a look at the chemical reaction that we know to be occurring. This is a carbohydrate. We're going to give it a generic formula of, let's call it CXHYOZ. And we're going to be burning this, and the component of atmospheric air that's necessary for combustion is oxygen. So we're going to be adding O2 to this system. And over here on the product side, the two products are carbon dioxide and water, as are the products of any combustion reaction of a hydrocarbon or carbohydrate. So that's kind of our starting point. And the big problem with this particular example is going to be the oxygen. Because number one, the oxygen is coming from two different places in our reactant side of the equation. That is, it's both present in the carbohydrate as well as present in the atmospheric air that we're burning it in. And it's also present in both of the products. That is, some of the oxygen finds its way into the CO2 as a product, and some of it finds its way into the H2O. So the suggestion I would make here is to recognize that oxygen is the problem, so we're going to save that to last for figuring out what's going on with oxygen. We'll start with the other two elements, which are carbon and hydrogen. They're easier to deal with. So let's start on the product side. What I'm ending up with here is 0.520 grams of carbon dioxide. And that is where all of the carbon ends up in this chemical equation. So I'm going to go ahead and set up a real quick monorail here. Monorail! To convert the mass of carbon dioxide that we got as a product here into some number of moles of carbon that must have been present in the system to begin with, because all of the carbon we started with ended up as carbon and carbon dioxide. So we'll go ahead and set up a quick conversion here. 0.520 grams of CO2 will then convert from grams to moles using the molar mass of carbon dioxide, which I happen to know is 44.0095 grams of CO2 per 1 mole of CO2. And then last step, and this is an important one here, 1 mole of CO2 contains 1 mole of carbon atoms. Please make sure that you're careful here in your unit analysis to get the exact value we're looking for here in terms of moles of carbon, not moles of carbon dioxide, even though the values are equivalent to each other here. So I'm going to go ahead and multiply this out here, cancel out my units, and we'll see here that I end up with a value of 0.0118 moles of carbon present. So I'm going to save that value. We're going to need that for our molar ratios later on here. And now that I've dealt with carbon, let's go ahead and do the same thing for hydrogen. All of my hydrogen in the product side is ending up here in the water molecules. So I'm going to go ahead and figure out how many moles of hydrogen I ended up with on the product side, because that must have been equal to the amount of hydrogen I started with present in my carbohydrate. So we've got from my given here 0.216 grams of water, converting from grams to moles with the molar mass of water of 18.01528 grams of water per 1 mole of water. And then last step here, this is important here, I have moles of water, but I don't want moles of water, I want moles of hydrogen. So for every 1 mole of water, there are 2 moles of hydrogen atoms in that water sample. So I've got now a value we can multiply out here again, do a real quick cancellation of our units, and we end up here with 0.0240 moles of hydrogen atoms present in this system. So I now know how many moles of hydrogen I've got, how many moles of carbon I've got. And as I mentioned, oxygen's the problem. So to solve that problem, I'm going to go ahead and make real quick 2 more calculations. First, converting my number of moles of carbon present into grams of carbon present. So I'll take that 0.0118 moles of carbon that we had there, and I'm going to go ahead and make a real quick grams to moles conversion, recognizing that in 1 mole of carbon there are 12.0107 grams of carbon. And that tells me that I had 0.142 grams of carbon present in my system. I can do the exact same calculation for the hydrogen. In my water molecules, there were 0.0240 moles of hydrogen present, and then we'll go ahead and say that per 1 mole of hydrogen, there is a mass of 1.00794 grams of hydrogen off your periodic table. That tells me that in this system, there are 0.0242 grams of hydrogen present. And the reason why I need to know both moles and grams here is this. I don't know how much oxygen there was present in the air that ended up in my CO2 and my H2O. But I do know the initial mass of the carbohydrate sample that I burned. And I also happen to know the amount of that sample now that was carbon and the amount that was hydrogen, because all of the carbon and hydrogen must have come from that carbohydrate sample. So if I simply subtract the amount of hydrogen and carbon that are present in the system from the initial sample of the carbohydrate there, 0.360 grams of carbohydrate minus my 0.142 grams of carbon minus my 0.0242 grams of hydrogen, that tells me that the remainder of that carbohydrate, the remaining mass of 0.194 grams, must have been the other element present, which was oxygen. So now I know how much oxygen in terms of mass was present in the initial carbohydrate sample. And I can simply go through and make a conversion from grams of oxygen into moles of oxygen by dividing 15.9994 grams of oxygen is equivalent to 1 mole of oxygen, which gives me 0.0121 moles of oxygen present in my carbohydrate. And now I find myself in the much happier position of knowing the moles of all species present in my initial carbohydrate sample. So now I'm back into more familiar empirical formula territory. So we've got moles. The next step would be to divide everything by the smallest number of moles, which in this case looks to me like this 0.0118 moles here. So I'll divide everything by 0.0118 moles, which gives me a ratio of 1 carbon to 1 oxygen to 2 hydrogens. And that now has got me my empirical formula then of CH2O. Not surprisingly, the empirical formula of a carbohydrate. It's essentially carbons bonded to what is essentially the ratio of hydrogen to oxygen within water. And then all that remains now to find my molecular formula is to make a comparison of the empirical formula mass to the molecular mass. So I can go ahead and do a real quick and easy calculation of our empirical formula mass here. We had, again, 1 carbon, a mass of 12.0107, 2 hydrogens, a mass of 1.00794 grams per mole times 2 moles of hydrogen present in 1 mole of the empirical formula of our carbohydrate. And then plus our 15.9994 grams per mole of that oxygen present there gives me an empirical formula mass of, looks to me like right around, looks like about 30 or so grams per mole. And I then need to go through and simply divide my molecular mass by my empirical formula mass. So the 180 grams per mole divided by our 30 grams per mole gives me a multiplication factor of 6, which means final cleanup step here, all I need to do is multiply my empirical formula by 6, which gives me the molecular formula of C6H12O6, the formula of a very, very familiar carbohydrate to you. That is the molecular formula of glucose. So you can see here, with a little bit of agility in our calculations, we can go through and make some higher level AP style calculations involving empirical and molecular formulas. So that is it for this lecture. Thank you very much for watching.